This one is called Wien bridge oscillators. We will also see the circuit construction or circuit design of this oscillator by using operational amplifier. Remember, I have the option, instead of using operational amplifier, I can also use the transistor BJT. You know, BJT, we have the NPN and we have the PNP. Okay, so I can use also oscillators to design this oscillator. I can also use the transistor to design this oscillator instead of operational amplifier. Okay, so any oscillator consists of two stages: amplification stage, feedback stage, and any oscillator must satisfy Barkhausen criterion. It means the gain multiplication must be equal to 1 and the phase difference between the input and output should be 0 degree or 360 degree. So this is the condition for any oscillator. So now we are going to see Wien bridge. So what this oscillator is doing, it can produce sinusoidal oscillations in the range of 1 megahertz signal frequencies. So you can generate maximum up to 1 megahertz at the output. 1 megahertz means what? 1000 kilohertz. 1000 kilohertz means what? 1 million hertz. So you are generating 1 million cycle per second by using this Wien bridge oscillator. That is the meaning of this one. So, okay, so it produces very stable oscillations. So that is very important property of the oscillator. You need to have the very stable oscillations. It means all these 1 million cycles must have the same amplitude, and then it will repeat again and again. So we have a very stable oscillations using from this Wien bridge oscillator. Okay, this is the circuit design of Wien bridge oscillator. So you don't need to get confused. So this is the operational amplifier and this is the RC network. Again, RC network, but we made in terms of bridge circuit. So if you look more closely this bridge circuit, so here you can see we have the series combination of resistor and capacitor. R1 and C1, they are connected in series. And we have another R and C, a resistor and capacitor, which are connected in parallel. So R1, C1 series and R2, C2 is in parallel. And this is the bridge. And here we also have two more resistors, R3 and R4. So R3 and R4 are really working like a feedback path for this negative input or negative feedback of this operational amplifier. So here we are not applying any external input. This one is generating thermal noise, and the thermal noise will be feeding to this operational amplifier, and this is just feeding back to this bridge circuit again. This is the bridge circuit, and this just go again and again and again. Then it's producing oscillations. Oscillations are sinusoidal signals. It's not non-sinusoidal signals, it's sinusoidal, because we know whenever we talk about the waveform based on the shape, so this is a sinusoidal. And what is non-sinusoidal? For example, you have the square wave. This is not in the sinusoidal shape. So we call this is a non-sinusoidal. So there are so many non-sinusoidal formations. You can use the square wave, or you can use the triangle wave, or you can use any other spike waves, things like that. So this is this bridge circuit is only producing sinusoidal signal up to 1 megahertz. So here just you can read this R1C1 and R2C2. This is the series combination, and this R2C2 is a parallel combination, are acting like a frequency adjusting elements. What does it mean? So you can have some particular frequency, 1 kilohertz, for example. If you want to change this one, you have to adjust the values of these capacitors here, or this R1C1 or R2C2 or both. You have to change the values. Then of course the frequency of oscillation will change because of the formula. We will see the formula in a while. And these R3 and R4, R3 and R4 are acting like a feedback stage for this operational amplifier. So observe closely. Output of an op amp is feedback to the bridge as an input. So output of the op amp, we are taking fraction of the output and feeding to this bridge circuit. And output of this bridge circuit. So here you can see here operational amplifier. We are giving the output of the operational amplifier as an input to this bridge, and then the output of the bridge circuit is given as an input to this operational amplifier. So here we are applying differential input. We are applying two inputs to this operational amplifier. We are not grounding this one. We are just giving the grounding is common ground is here in order to have the complete current flow. But we are getting the two meeting points or two junction of this bridge circuit and feeding to two input terminals of this operational amplifier. So this is the circuit construction of or circuit design of this Wien bridge oscillator. So just to remember the circuit construction, now we will see the circuit operation, how the circuit is working. So I redraw the same Wien bridge oscillator with little bit different in a different style. So let us see here, maybe let us see here first. I told you here we have the 1 R2 and C2 is the parallel combination, and 1 we have the series combination. So here we have the series combination and here we have this parallel combination. So this series combination, I put it here in this feedback path. This is the positive terminal. Remember, whenever we give the positive feedback to this operational amplifier, this will be very unstable. That is why the negative feedback is very, very important in any operational amplifier. So here we have this negative feedback using this R3 and R4. So here we have this R3 and R4. We are feeding back to this negative. The other end of the R4 is grounded. So this is what here. Okay, here I think the number got changed, but this is the feedback transistor. The other end is grounded via this R3 transistor. And here in the positive feedback, we have one circuit, parallel circuit, RC network parallel combination, and we have RC network series combination here. And here we are taking the fraction of output and then feeding back again to this negative input terminal. This is also short circuited. So the same circuit we can redraw in this way. So just by rearranging the components. Thermal noise. Thermal noise of the circuit has multiple frequency components that we know that, because this kind of circuit is producing some thermal noises. It has multiple frequency components, but the RC network selects a specific frequency to achieve sustained oscillation. So here, if you observe more closely, the series RC network acts as a high pass filter. So here, this is the R1 and C1. We are connecting in series. So this is acting like a high pass filter. And the parallel combination is acting like a low pass filter. So even though the thermal noise have multiple frequencies naturally, so this low pass filter will allow only low frequencies, and the high pass filter will allow only high frequencies, right? So then, so that is the difference. So we are selecting certain frequency. So we are selecting certain frequencies and then we are producing at the output. So LPF, okay, so low pass, this is do allow, does allow. So we will get only a specific frequency at the output. So remember the band pass filter. We already studied about band pass filter and band stop filter. In the band stop filter and band pass filter, we are just using the series combination of the low pass filter and high pass filter. We are just cascading this and we get at the output band pass. Here we are using the summer together with the LPF and HPF. And we have the summer, we are giving output to the summer or summing amplifier. Then we get at the output BSF. It means we only stop certain band and then allow all other frequencies. Band pass means, so when you connect these in a series combination or cascading mode, then it will be filtered these low pass frequencies and high pass frequencies. It will only pass certain band. So in that case, so this is just the same low pass filter and high pass filter acting the opposite way. If you only use this as a low pass filter, of course, this will only pass the low frequencies and the high pass filter will only pass the high frequencies. But if you use in this kind of combination, then what it will do, it will not pass this low frequency, it will not pass the high frequency. So whatever the frequency in between, the intermediate frequency, that will be passed. Then this is correct. So you should know the difference. It's really where you are using this R and C, then it will act differently. So when you use this in this kind of cascade mode, then this will not pass low frequency and this will not pass high frequency, and it will pass only the between frequencies. Remember, we have the cutoff frequency 1, cutoff frequency 2. So okay. So this will allow only a specific or selective frequency to this operational amplifier. Then this will amplify and we get at the output the stable oscillation. Okay, so now for this circuit, the standard value of beta is equal to 1 divided by 3. So the beta is the combination of, sorry, this is the gain of this feedback network. So here we have the feedback network all the way. I have to change my color. So this is the feedback network. The feedback network gain is 1 divided by 3 to satisfy the Barkhausen criterion. So the A value must be equal to 3 because A beta is equal to 1. Beta is 1 divided by 3. It means A must be 3 in order to satisfy this Barkhausen criterion. And this feedback network will provide 180-degree phase shift. And this operational amplifier will provide 180-degree phase shift. So output we get 360-degree phase shift. So Barkhausen criteria is satisfied. And also this network A beta is equal to 1. And if you want to change the frequency of oscillation, then you can change the value of these capacitors. For example, C1 and C2. You can also change the R1, R2 if needed. Let us see here. We know that gain of the non-inverting op-amp. So this is, we are using this operational amplifier in non-inverting mode. Remember, we are applying the input to this plus terminal, and the minus terminal is grounded. So the output of this kind of combination of non-inverting operational amplifier is 1 plus R4 divided by R3. So R4 divided by R3, feedback resistor divided by this grounded resistor. And we know this 3, A value is 3. In order to get satisfy the Barkhausen criterion, A value is 3. So we are replacing here 3 is equal to 1 plus R4 divided by R3. So R4 divided by R3 is equal to 3 minus 1, that is 2. Or we can rewrite this equation, R4 is equal to 2 times R3. So when you design the circuit, this is the circuit design of this Wien bridge oscillator. So you can change these values based on whatever the oscillation you want to achieve. But this R3 and R4, you have to be careful when you choose the value, when you design the circuit. R4 must be 2 times of, then yeah, all the conditions will be satisfied and this circuit will produce oscillations in a stable way. Now we will see the formula. So we know this is the circuit of Wien bridge oscillator. It doesn't look like a bridge. That's why we have the bridge here. You know, later maybe you will study about the bridge rectifiers, half wave bridge, full wave bridge rectifiers, and so on. So whenever we connect the circuit like this, components like this, we call this as a bridge. So that's why we call this a Wien bridge. Just for our understanding, we rearranged the components in this fashion. So frequency of oscillation of Wien bridge oscillator is FR is equal to 1 divided by 2 pi square root of R1C1. So this is the R1C1 and R2C2. Okay, so this is the formula for frequency of oscillation. So if R1 is equal to R2, if R1 is equal to R2, and if C2 is equal to C1 or C1 is equal to C2, then what will happen here? So it will be R square and C square, right? Then we can take out this square root. Then the formula will be F is equal to 1 divided by 2 pi RC, the same cutoff frequency formula. So you can calculate the frequency of oscillations at the output by using this formula 1 divided by 2 pi RC. If you use the same value, for example, you use the 1 kilo ohm here, and you can also use the 1 kilo ohm here. And if you use the capacitor value, maybe 10 nanofarad, and you use another, okay, so this is the capacitor. So the capacitor value will be 10 nanofarad. So you use the same value of capacitors and resistors, then you can use this formula. So by adjusting these R and C values, you can change the value of the frequency of oscillation. So frequency of oscillation, again, I'm mentioning, so whatever the frequency you are achieving, how many number of cycles you are achieving per second, that is the frequency of oscillation. So by changing this value, then you can change the frequency. So now here is one small problem. So you can find the frequency of oscillations of this below circuit. So this is the Wien bridge oscillator. So why? Because we have one parallel circuit here, and we have one series RC circuit here, and this is connected to this positive terminal, and the negative terminal is grounded via this grounding resistor and then this feedback resistor. So here you can see 10 nanofarad and 10 nanofarad for the capacitor. R1 is the same 10K, 10K. And here feedback, you can see here is R4 and this R3. It's 2 times of this R3. So now the frequency of oscillation is very simple, 1 divided by 2 pi RC. So you can calculate this. It's just a very simple and straightforward calculation.